Now we'll discuss about statically indeterminate problems. So in statically determinate problems, the number of unknowns is equal to the number of equations which you get from statics. Suppose here this is a cantilever beam, and here there is one reaction force and one reaction moment, and by applying two equations of statics, that is summation of force in the y direction is 0, summation of force in the y direction is 0, and the sum and moment about any point is 0. So these are the two equations. Because summation of forces in the x direction is 0, that is true, but that gives you a 0 equal to 0 equation. So the two equations which you get from statics are summation of forces in the y direction is 0 and summation of moment about any point is 0. So there are two equations of statics, and you get two unknown support reactions here. So if these forces are known, then you can find out the reactions from equations of statics. Now suppose we put a roller here. Then what happens? From this roller, another unknown reaction will come which we do not know. So there will be three unknowns and two equations. So it becomes a case of a statically indeterminate problem. Now Castigliano's theorem can be applied for statically indeterminate problems. So how can we do that? So we have to remove this support, and we have to show the support reaction instead. So let R be the support reaction. Now we have to calculate the strain energy as a function of all the applied forces, whatever, and also this R. Now if we do del U del R, then what does that mean? That means the displacement or the deformation in the direction of R at the point of application of R. That means in the direction of R at the point of application of R. Now this being a support, this has to be 0. So along with the equations of statics, you are getting another equation. So now there are three equations, and you can solve for the three unknowns. Now it does not matter how many unknown support reactions are there, because in this case there is one redundancy, that is number of unknowns is 1 greater than the number of equations. Here the redundancy is more than 1, because here the number of unknowns are 2 support reactions here plus 3 unknown support reactions here, so it is 5, and there are 2 equations from statics, so the redundancy is 3. But here what we have to do is, you have to just show the forces, reaction forces coming on the beam from these supports, and just by doing del U del x equal to 0, del U del y equal to 0, and del U del z equal to 0, you get 3 more equations. So never remove a support and replace it by a reaction from a statically indeterminate structure. So sometimes we think that in a statically determinate structure, suppose from that we remove one reaction, suppose from that we remove one support and show the reaction coming from the support, but that is not permissible. So at least you have to keep the reactions which are obtainable from equations of statics, so that the structure remains stable. Okay, so the structure must be adequately supported. So in this problem, there is a thin semicircular arc ring of mean radius r. capital R. That means this is the mean radius, capital R, is pin supported on unyielding foundations. So this is pin supported at unyielding foundations at A and B. Unyielding means rigid foundations at its ends A and B, and carries a vertical load P at the crown C. So this is the crown C, and at the crown C there is a vertical downward load P. So using theorem of Castigliano, find the horizontal component H of the reactions at A and B. So since this problem is a symmetric one, that means the geometry is symmetric and so are the loads. So this problem is symmetric, so the reactions will also be symmetric. So in this pin joint there will be one X reaction and one Y reaction. Here also one X reaction and Y reaction. So there are so this H should be this H, that also you get from one equation of statics, and the summation of these two X should be P, that you get from other equation of statics. So X will be equal to P by 2, but you do not get the value of H. So this is a statically indeterminate problem. So for that what we do, we have to cut it somewhere here, and we are showing the free body diagram here. So this is X, this is H, and here from, since this is in static equilibrium, X will come and H will come, so this maintains the force equilibrium. But since the point of application is here and here the point of application is this point, so there will be a moment, and if you compute moment about this, m clockwise moment about this m clockwise moment plus H into R sine theta minus X into R into 1 minus cos theta. So m is X R1 minus cos theta minus HR sine theta. So I strongly suggest you that you write the moment equation like this: m clockwise plus HR sine theta, HR sine theta about this point is also clockwise, but X is giving anti-clockwise moment, X R 1 minus cos theta, that is equal to 0. So from that you get m as this. Now now see, from symmetry, this is, if this angle is theta, so from theta equal to 0 to pi by 2, you compute the strain energy and then you double it to get the strain energy in the whole of the arc. So that's precisely what is done. 1 by 2 EI, it is multiplied by 2, and the integration is done between 0 to pi by 2. So you do not, please do not carry out the integration from 0 to pi, because the bending moment expression changes after this P is applied. So the bending moment expression from 0 to pi by 2 and from pi by 2 to pi, they are not same. So it's always advisable to compute the bending moment from 0 to pi by 2 and double it. So now del u del x is 0, because del u del x is 0. So m is coming in terms of m is, this is m square. So, and you know that x is pi by 2, so m is coming in terms of this. So here you replace x by p by 2, yes, and you put that here, and here you compute del u del h equal to 0. del u del h equal to 0, and here, so while computing del u del h, you just take the differentiation within the integration, so this becomes twice m del h. So that's it. That is convenient because the expression becomes simpler. So if you do that, so you get an equation like this. From there you can compute your h. So the next example is this, a wood cantilever beam. So this is an wooden cantilever beam, 1.5 meter long and having a rectangular cross section of 10 centimeter wide and 15 centimeter deep, is built in at B. So this is built in here and supported at A by an inclined guy wire. So this is an inclined guy wire. The beam has a modulus of elasticity, that means the modulus of elasticity of wood is this, and the guy wire has a modulus of elasticity 21 E5. This, the guy wire is steel actually. So this is a steel guy wire and this is the wooden cantilever beam. So, and the cross sectional area of this A1, the cross sectional area of this guy wire is 0.333 square centimeter. Find out the tensile force induced in the guy wire. So what is the tensile force here in the guy wire? That is what is to be found out. So again, this is a statically indeterminate problem. So what we do, we just cut the wire here just at point C from the support and we show the force S. So if this is the force in the guy wire, then if you draw the free body diagram of the beam, so here P and here S, this angle is given as 30 degree. So the net downward force is P minus S sin 30 and net axial force, axial compressive force is S cos theta, and here you will get a reaction and a reaction force and a reaction moment. So this completes the free body. And what is the strain energy stored in it? The strain energy first, the strain energy stored in the beam. So this beam, this is the force, this is the transverse force at the end of a cantilever beam. So you know the cantilever beam, if a force is applied, in the cantilever beam, here the deformation is, if this force is P, then the deformation is PL cube by 3 EI, PL cube by 3 EI. So here, since we have applied a force of P minus S sin theta, the deflection is P minus S sin theta L cube by 3 EI. So W for wood, W subscript for wood. And what is the force? So half P into delta. So the force is P minus S sin theta and delta is PL cube by 3I. So this is the bending strain energy. This is the bending strain energy stored in the cantilever beam. And what is the strain energy? This will be subjected to axial strain energy. That means P square L by twice AE. So this is P is S cos theta. So P square L by twice AE. So this is the axial strain energy, axial tensile strain energy stored in the guy wire. And this energy is S cos theta is the force on this, so this will also get compressed, and the energy of compression is S cos theta p square, S cos theta whole square for p square. L is the length of the beam, and by, sorry, I made one mistake. So this is actually, this is L, so I made one mistake. So this is L, so this is L, and this length is L by cos theta. So the strain energy stored in the guy wire is S square L, L is L by cos theta by twice S steel S steel. So this is the tensile strain energy in the guy wire, and this is the compressive strain energy S cos theta p square L, S cos theta whole square L by twice AW EW, W for wood, cross sectional area wood, and modulus of elasticity wood. So this is the bending strain energy for cantilever, this is the axial strain energy for cantilever, and this is the axial strain energy for guy wire. Now we use del u del s equal to 0, because this point has got no deformation, this point has got no deformation in the direction of S, because this is tied here, so this cannot have any deformation in this direction. So del u del s equal to 0, and this gives you this value for S. Now if you replace the numerical values, you get S equal to 1.48 P. Now you may wonder, so for the cantilever beam, so what we could have done is, so this is the cantilever beam, and here there is a load of P minus S sin theta. So what we could have done is, so here we could have showed the support reactions, then we could have cut here at a distance x, then we could have shown the bending moment here, and we could have integrated m square dx by twice EI over the whole length of the beam. But that would have given you the same expression for strain energy if you just directly multiplied the load, this is the load, and this is the deflection at the point of application of the load in the direction of the load, and half here. So you would have get the same expression for the transverse bending energy, bending strain energy. Okay, so let's stop here.